Hello, we are going to talk about reactions that occur in aqueous solutions. So what we're really curious about are net ionic equations. Our objective is to learn to write net ionic equations, and we want to understand what information a net ionic equation can contain. So the first thing we need to take a look at is water. Aqueous reactions mean that whatever reaction we're observing is happening in solution, mainly a solution where the solvent is water. So there are two different chemicals dissolved in water potentially, and then well in water they react. This is extremely important because the surface of the Earth is roughly 70% water. Okay, and in the human body, you are about 2/3 water, and in this case, we see Mr. Miller is about 2/3 full of water there. All right, so there are lots and lots of reactions that happen as aqueous reactions that happen in water in solution. There's a lot of important chemistry that we need to understand these reactions. So we're first going to look at a complete ionic equation. This is not the same thing as a net ionic equation, but to understand net ionic equations, we need to understand complete ionic equations. A complete ionic equation is an equation that shows dissolved ionic compounds as dissociated free ions. So what that means is if we were to write a compound with a little aq after it for the state of matter, instead of leaving that together as one whole ionic compound, we would separate the cations and the anions and make them part of their own piece of the equation that we're writing. So if we look at this reaction, which is one of the same reactions studied in the double replacement video, we see that the two reactants are aqueous. Okay, one of the products is aqueous and one of the products is solid. So instead of leaving those as complete ionic compounds, what we do is break them up. And I've just done the first half here because it starts to take up a little more space when you do this. But you can see we've broken up the barium chloride into a barium 2 positive ion, and we've taken the chloride ions and noted that there are two of them, so gave it a coefficient of 2, and it has a 1 negative charge. The magnesium sulfate was split up in a similar manner. If we look at the products, you can see that barium sulfate is still simply one ionic compound. Since it is solid, we cannot break it apart. We only pull apart the aqueous components of the equation. So magnesium chloride, again, on the product side, is aqueous, so we do split that up into magnesium and chloride ions, excuse me. So if you looked at this all together, this would be a complete ionic equation. We just have the reactants and the products on two separate lines. Spectator ions. So here are a couple of key vocabulary words that we need to understand moving forward to net ionic equations. A spectator ion is an ion that's on both sides of a complete ionic equation. Also, it's not directly involved with the chemical reaction. That means it doesn't break bonds and form new bonds. Okay, it's not turning into a new compound or a new element. A net ionic equation is an equation for a reaction in solution that shows only the particles involved. Okay, so we are going to omit the spectator ions. That is the difference between a complete ionic equation and a net ionic equation, is we need to identify the spectator ions and remove them from the equation. So here we have the complete ionic equation that we developed a couple of slides ago. We need to try and identify spectator ions. So take a moment. Which ions appear on both the reactant side and the product side. The first one I note is chloride. I've now highlighted those in red. So you can see that chloride is present on both sides. It's not actually chemically changing by forming new bonds or breaking bonds. So we can identify that as a spectator ion. There's another one. We can identify magnesium 2 positive. It appears as both a reactant and a product. So it's not involved in the chemical reaction, so we can remove it. To make the net ionic equation, what we do is simply take out all of the spectator ions. So as a reactant, we still have barium 2 positive and sulfate, which is a 2 negative ion, and we place those on the reactant side. On the product side, there is only barium sulfate, and so we place that in as the lone product. So this is the process for going through and turning a complete ionic equation into a net ionic equation. One more important thing to consider is we need to certainly make sure that the number of atoms and ions on each side are balanced to follow the law of conservation of mass. But we also need to make sure that the net ionic charge is equal on both sides. So if we look at the previous reaction, barium is 2 positive and sulfate is 2 negative. The left-hand side, or the reactants, give a total ionic charge of neutral or 0. Barium sulfate, being a solid ionic compound, also has a charge of 0. So these sides balance. Okay, they balance both in terms of the law of conservation of mass for number of atoms, as well as ionic charges. An example of one that does not necessarily balance is solid lead reacting with silver nitrate. So here we have a single replacement reaction. If we turn it into a complete ionic equation, we get this by simply splitting the silver from the nitrate and the lead from the nitrate. We can identify nitrate as a spectator ion and remove it. Now we have the start to a net ionic equation. There's one lead atom on the left-hand side and the right-hand side, and one silver atom on each side. However, if you look at the total charge of the reactants, we have 1 positive from the silver and nothing from the lead, and then on the product side we have nothing from the silver and 2 from the lead. So the total ionic charge on the product side is 2 and the reactant side is 1. This is an issue. What it indicates is there have not been an equal number of electrons accounted for on each side. So we need to balance this. So we'll take that same chemical equation, and I'm going to put a 2 in front of the silver on the reactant side. What this does is it allows us to get the net ionic charge on the reactant side up to 2, and then we are equal to the ionic charge on the product side. Now we need to put a 2 in front of the silver on the product side to balance out the number of atoms on each type. If you look at this final statement, the number of atoms of each type balance for both the reactants and the products, as well as the total ionic charge for each side. A net ionic equation shows only the specimen involved in the reaction and is balanced with respect to both mass and charge. The types of reactions you're going to find this in are double replacement reactions and single replacement reactions. Of the 5 types of reactions we've studied, these 2 will be the ones that we can look at in aqueous solutions.